So my name is Jake Hendley. I'm here to talk about software in the EV space. Really just want to provide like a high level kind of technical landscape of the different like integration points and actors and everything else that kind of consist of the global EV charging network. And I say charging because this talk is going to focus more on charging and energy transfer to the vehicle than it will on like what an EV is. That said, I'll have a couple slides talking about different types of EVs because I think they're cool, and we'll kind of go through that. So, quick overview, we'll talk about chargers and vehicles. We'll get into some of the data sources that enable this like globally connected EV charging approach. We'll talk about standards bodies. A lot of this is going to be a little bit dry, but it's important to have the kind of background and context for who is who and what is what in the industry. Then we'll get into the two big protocols that enable everything and allow you to kind of charge. We'll get into use cases, and then if we have time at the end, we'll talk about some really cool software-enabled features, some of which are newer and coming out, some of which are already there. So, starting with chargers. Chargers dispense energy to electric vehicles. If you don't have an EV, you've probably seen them. They're growing. There's hundreds of thousands all over the world now, and they really come in three forms. The first form is your household outlet. So you get an extension cord, you get a little adapter on it, you run that cord out to your car from your house, and it takes like 3 days to charge your car. Most times you'll see this when somebody is new to EVs or they're waiting to get their charger installed, or maybe they have really good access to a fast charging network, or they charge at work or something like that. But I would say this is probably the most common because it comes with vehicles, right? They come with the adapters and everything else. Next most common when it comes to dedicated hardware for chargers, this is the most common type of charger, is AC. They typically vary in power between 11.5 and 19.8, and I put the amps there because it's typically 48 or 80 amps. In the electrical engineering industry, which I'm not classically an electrical engineer, but you learn things as you go with this kind of stuff, the rule is you should never exceed 80% of a breaker, and standard breakers are 60 or 100 amps, and so chargers are manufactured at 48 and 80 amps. So again, these are like, it might take you overnight to charge your vehicle. These are kind of the most prolific chargers. These are your Tesla chargers. If you're around downtown Greenville, they got a bunch of Clipper Creek chargers in the different parking lots. That's what that is, AC charger. And then you get into DC fast chargers. Now these are the big boys, right? Anywhere from 50 kilowatt hours or kilowatts to 350 kilowatts. And that upper bound is still growing. Like eventually we'll have gigawatt charging, or megawatt, I guess first. So as opposed to the previous one, these are $500. You can get some really fancy ones for a couple grand. These to get in ground can get up into the millions, right? Because you got to retrofit your infrastructure, get dedicated energy, working with utilities and all that. So that's kind of the landscape of chargers, if you will. All right, so let's talk about vehicles. I'm gonna go through like 4 acronyms for different vehicles that have batteries on them. So the mild hybrid is the Prius of the world. Got a little note here as well. Something I think is kind of cool is it's also the luxury supercharged vehicles, because they figured out with a battery and a supercharger combined, you get extra propulsion and extra energy delivered to the wheels at both low RPMs with the battery and high RPMs with the supercharger. So that's where a lot of mild hybrids are coming into existence as well. One step further from that is plug-in hybrid. Same kind of concept as mild hybrid, normally about the same size battery, but it's got a plug, right? So I think the vehicle, most models will still kind of charge the battery through the engine, but it also has the ability to like plug into a dedicated AC or DC charger and top up that secondary battery really quick. Then we got BEVs. So, and I should have updated the subtitle on this one, big old batteries. So the BEVs are vehicles that exclusively have a huge battery. Normally it's the entire underbody of the car, and the car is built around the battery. Anywhere from like 50 kilowatt hour batteries up to, I don't know what the max kilowatt hour capacity is right now, but that's the bread and butter here, and that's what I focus on in my job primarily, is vehicles who are exclusively propelled by energy from battery. And then lastly, you got This doesn't really exist yet. I think there's one model out, it's like supercharger from Ram or something like that. But these kind of take the mild hybrid approach and turn it on its head, where the vehicle is propelled by a battery, but then you got like a 4-cylinder generator that is effectively an engine, and that kicks on operating at optimal RPMs in theory, recharging that battery. You can get like 600-700 miles of range out of these. I think the big holdback here is they're very inefficient because you're transferring energy from battery to engine to there's a lot of jumps in that flow. So those are really the 4 vehicles. Again, we're not going to get too deep into what all that means. We're mostly going to focus on charging and how we move energy around in light of EVs. So data sources. Number 1 is charger data. Almost all chargers, other than all those Clipper Creeks you see in downtown, those are the dumbest, best working chargers I've ever seen. They always work, but they don't send data anywhere. They're just an on-off switch, right? In general, the industry is moving more towards smart charging, and that requires chargers to have cellular and or Wi-Fi capabilities to send a bunch of data to the cloud. We'll get deeper into this, but they send meter values, when it starts, when it stops, session information, that kind of stuff. And then you got vehicle data. It's a natural complement to charger data because both of those two things are part of the same problem. There's really 2 flavors here. This isn't super important, but I think it's neat. Vehicle data, like almost every vehicle coming off a line now has a cell modem in it, has native telematics sending data home to the mothership, right? And then there's a second type, which is PID-based. And I put examples here, Geotab and Samsara. Unless you're heavily involved in like the commercial fleet space, you probably haven't heard of them, but they're quiet unicorns, like billion-dollar companies that provide PID-based telematics, which all it is just like a little rectangle like this, got a cell modem in it, plug it into your OBD2 port on your vehicle, and it starts sending data up to the cloud. You can build integrations against that. You can install that across multiple makes, so you can get multi-make kind of data flowing into your system. That's how that works. So, short recap, charger data, vehicle data, 2 most important things there. All right, here's the dry part, standards bodies. I'll preface this by saying, in a world where like EVs are prolific, they're all over the globe, in order to move forward in this problem space, you have to have standards. And that comes with caveats, right? Standards slow things down, but it makes sure things are done correctly. I have this inner monologue all the time because I kind of hate how it slows it down. I want to build things, but I see the benefit of these too. So let's talk about the big one, Open Charge Alliance. And it's the governing body behind these 2 acronyms. You'll also notice that it's a world of acronyms once you get in here. But these are the 2 primary protocols that interact with chargers, and we'll get more into that in a minute, but this is a great standards body. They're the reason that we have these standards, and they spun off from the company ChargePoint. I think they're pretty cool. All right, then you got SAE. So Society of Automotive Engineers does what it says on the can, right? They care about specs for the vehicle. I put J1772 here as an example. That is actually the standard behind the plug that most vehicles now, most electric vehicles have. There's other variations, like the Nissan Leaf has this CHAdeMO plug, which is about this big. Tesla released their plug as a North American charging standard. Really kind of assuming everything goes that way because Tesla was the first and best one in this business. But SAE does things like, provide specs and design parameters for J1772. You got ISO. ISO is more generic standard organization. There's a few really important ones in here, like 15118-20, which helps govern charger to vehicle communication. We'll get more into that at the end if we get to some of the cool stuff like vehicle discovery. But in general, I think a lot of folks in the software industry have heard of ISO because there's ISO 27001, which is all about like infrastructure security, application security, and it marries with SOC 2 compliance and some stuff like that. I don't want to get too deep there. It also designates things like you must use TLS 1.3, right? Okay, so we talked about data, standards bodies. Now we're going to get into cool stuff. So OCPP. OCPP is the Open Charge Point Protocol. It's really just a WebSocket connection between charger and cloud. And this is the spec it's a communication spec very specifically that governs like what is the schema and what is the cadence of messages you need to send or receive from that charger in order to control it. So I've got 3 big ones up here, and I think like the spec is hundreds of pages long. But just to call out 3 kind of primary elements of Open Charge Point Protocol. Configuration is the first one. Chargers in the ground. There's a bunch of different configuration elements. I'll show a pseudo example here in a second. But this is things like what is the max amperage this charger should put out? How often should the charger phone home, right, to the cloud? Then you get into authorization, and that's really answering the question of should this charger dispense energy. So it's not like, is the connection between the charger and cloud secure? This is more like somebody's trying to dispense energy from this charger. Should we let it happen? And there's half a dozen, maybe a dozen different authorization mechanisms that can be put in place to say yes or no accordingly. And then lastly, assuming it's configured and authorized, there's transactions. And that's like all the information that goes from charger to cloud while it's charging. I think this is okay, so here's a pseudo example. Actually doing this stuff is more complicated. There's gonna be more configuration, more thought into authorization, but just for illustrative purposes, here's a set configuration. So this is saying, tell the charger to send meter values every 60 seconds. And this is all in the spec. We've got that long-lived WebSocket connection, secure WebSocket from our servers to the charger, and we're telling it we want it to phone home while charging every 60 seconds. So we configure it. Then we do a remote start. So not to get too nerdy in here, there's 2 ways to kind of initiate a charge. The charger can detect when it's plugged in and then proactively reach out to the cloud and say, should I start? Or the cloud can say, hey, if you're plugged in, start charging. So in this case, we're doing a remote start, meaning cloud telling charger to start charging. Importantly, it says connector ID here. Most chargers you'll see have 1 hose with 1 plug on the end. But there are some that have as many as 3. There's certain like parent-child situations where you can have a stack of chargers, all of which are in theory 1 charger, but have multiple connectors, that kind of stuff. So we've configured it, we've remote started it, and now we're starting to get meter values based on that 60-second interval. And so this meter value tells us a bunch of really cool stuff in real time about the charging session that's happening, all about really energy, right? There's different readings, really in different values up here. We'll focus on the amperage down at the bottom, and I want to talk specifically about this measurand. So this is an important concept. The current.import, this is saying that the charger imported 15.2 amps. So when a charger tries to get energy into a vehicle, it doesn't push it, it can't push it. What it can do is offer energy. And so when you send that remote start or other messages, you actually configure it to say current.offered. This is saying, okay, well, regardless of what you offered the charger in terms of amperage, it imported 15.2, which is a little lower than I would expect. You would expect closer to 48, depending on the use case. But again, sample data from AI. This is not real data. So yeah, that's pretty much OCPP. I know I'm going a little bit fast. I'm trying to get all the way to the end of the talk. So let's talk about OCPI. So OCPP is cloud to charger, right? It's how we control individual chargers or chargers in groups. OCPI is how do you let the public know about chargers? So it's kind of that charger servicing element. And there's 4 parts to this. Similarly, again, the spec is hundreds of pages long. This is really just for illustrative purposes. But OCPI is a spec that enables communication between charging networks and service providers. Going back into acronyms, there's a bunch more. I'm not going to be technically correct in this because in theory I should be talking about EMSPs and CPOs and all that stuff, but that's just jargon. And we all know that like there's a charger, there's a cloud. I'm going to talk in that frame. With OCPI, so specifically OCPI declares a set of endpoints that you surface in order to tell the general public or consumers of your OCPI system about chargers, either like where they are, what's happening with them, what they've done in the past, that kind of stuff. We'll focus on these 4 Locations being the big one. If you've ever charged your vehicle and you pulled out an app and you've seen chargers on a map, for that matter, if you've used Google Maps and seen the little like EV charger icon somewhere, that information was propagated to Google Maps via OCPI's location endpoint. So that's how that works. Beyond location, so that's like how you get initial visibility into where chargers are and whether they're available. It tells you like this charger's in use, or this charger's available, or it's reserved, or so on. You get into tokens. So I don't know if Google Maps has this, but the application itself can initiate a charging session. The result of clicking like start charging my car on that app is it goes the opposite route from locations. So as the CPO or as the cloud that provides these locations, we're surfacing that up to the world. The world who controls that sends us back a token. We'll show some examples of this, but this is like authorization to start charging, kind of like I said in the previous OCPP, and that all marries together. Then we have sessions. This is live real-time information about what's happening at the chargers, like how much energy has been dispensed. Show some examples of that. And this last one is CDRs. If you're in any way associated with the electric vehicle space, you will hear CDR said more than anything else, because that's all business people care about. It is charging detail record, charger data record, a couple different definitions for that. It's the historical records of what has happened to that charger, including money and energy and all the things that the rest of the company that's not engineering cares about. So a couple examples. All right, here's locations. So with OCPI, again, you're surfacing these endpoints and the aggregators are grabbing them, and you're providing enough information for it to be relevant to the end user through this kind of network of different aggregators and actors in the charging ecosystem. So in this case, we've got locations, so obviously the address, lat long, all that. Then you get the EVSEs, again, acronyms for days. Electric vehicle supply equipment means charger. In this case, we've got two. So this one has a connector that's kind of down, but this one's reservable and it's available. And then this other one gives more information about AC 3-phase and all that. In general, this is like all the information you can provide about a single charging location and all of the chargers available therein. All right, tokens. I am a little behind. Tokens. This is the alt stuff. In this case, it's RFID. More often, this is going to be like credit card successful. We put a pre-authorization hold of $50, right, to tell the person controlling the charger they can dispense energy based on that pre-auth amount. Sessions, live information. So, which one? So you can tell like total cost down here. There's charging periods in there. There's a bunch of information about what's happening. And then finally, CDRs. This document is much larger, but this is really what is most salient here. You got energy and time that was dispensed as part of this charging period, total cost, total energy, and so on. Okay, so that was all the background. You got OCPP, OCPI, all the standards, bodies, and data structures and all that. Now let's talk about use cases. There's really three main use cases. You got home charging, which is probably the simplest. You got fleet commercial charging, which is probably the most complicated, but also the most boring, unless you're in that specific industry of commercial electric vehicles. And then you got public charging, which is your Tesla stations. If you go to the Ford station, or if you go to the Ford dealership on Lawrence, you'll see a bunch of big chargers there. That's a public charging installation, right? So we'll talk through these real quick. Home charging, again, the simplest, but kind of cool stuff. Time of use charging. Energy is most expensive, 5 minutes. Energy is most expensive from 4 to 7 p.m., so don't charge during that time. Plug the car in, but have a system that's intelligent enough to wait. Driver reimbursement. If you work for a company, you charge a vehicle at home, then they can reimburse the energy that was put in that vehicle, that kind of stuff. So, all right, we'll marry it together. I don't think I'm gonna get to the future features, but this is pretty interesting in and of itself. This is what public charging looks like. So as the primary charge point operator, which is the cloud that controls the chargers and surfaces the OCPI endpoints, you sit over here, an EV driver finds your charger on an app, up there at the top, you got EMSPs. Those are the ones that aggregate all the different charge points and networks to make them available on this app. That controls payment, that controls authorization, a bunch of other stuff. And so, user clicks go on that. Via OCPI, we get the token, and then we control the charger to start dispensing energy. So in a nutshell, that's pretty much it. There's a lot of other tails here. There's some that's like we have integrations with utilities because we want to know like what the specific rate is for, or what's the cost of energy, and a few other things. Let's see what else we can get through. This is another interesting one, again, commercial stuff. So you got a depot, which is like a parking lot for delivery vehicles if you want to paint a picture in your head. There's a panel, and there's 3 chargers on that panel. On the other side of that, we have the 3 chargers being controlled by our central management system. And what that can do is really fluctuate how much energy gets dispensed, or when the chargers output energy based on this panel, the cost of energy, the depot needs. Like, you can take all of those different variables into account and provide guarantees for vehicle uptime, which is really all fleet managers care about. And you can also provide cost savings and all that. All right, we might be able to get through a couple, 4 minutes, all right. Software-enabled features. So this is the cool stuff, and some of this stuff kind of exists, but some of it's a little bit futuristic. Plug and charge. So this is very cool. The idea behind plug and charge is to make it simpler to charge your vehicle than to go to a gas station. So if we go back to this, instead of this app being in play during the charging session, when you first get the vehicle, either you or your dealer or the OEM register it with a plug and charge capable network. And so when you get to the charger as this driver, you just plug in and walk away. Behind the scenes, we've installed certificates on the vehicle, like actual SSL certs on the vehicle, doing mutual TLS to the charger, where we also put certs. And then we have that backed by a payment provider. So it's all transparent to the user though. They just plug in and walk away. That's the best experience you can have. So that's plug and charge. Energy arbitrage is also very interesting. So if you think about vehicles as big batteries, and you think about arbitrage as like buy low, sell high, right? Energy is most expensive from 4 to 7 p.m. and is cheapest from 2 a.m. to 4 a.m., right? In theory, you could pull a bunch of energy into your battery from 2 to 4 a.m. and then sell it back to the grid from 4 to 7 and make money, right? Various levels of adoption here. Most of this is behind NDAs and so on and so forth. But this is becoming a bigger thing in the EV industry, is arbitrage. As we can move, because they're really mobile power plants, right? Not to use too much of a marketing term around EVs and their big batteries, but it's it's just a bunch of energy storage. So that's kind of cool. V2G, V2X, again, and all this is supported by software too. I want to focus on that. Like everything we just showed, Node, Nest.js apps in Kubernetes, global clusters, WebSocket connections, all the same, load balancers and everything else you would expect. Is really just a highly energized IoT deployment. So tens of thousands of chargers with just more energy than what you would expect on a normal IoT deployment. And the same device life cycle, all that other stuff that you've got to do. V2G, V2X is also very interesting. This is, again, like you've got energy in the vehicle. You can use it to propel that vehicle and do what you need to do, or you can dump it out of that vehicle for one reason or another. V2G stands for vehicle to grid. This is kind of that arbitrage example I used. If there's if the utility is expecting to have a brownout or they're having issues with the grid, you can supplement that by dumping all the energy from your vehicle back onto the grid. V2X really just says you can put that energy anywhere. If you want to run your house on that energy, you should be able to do that. So V2X is wherever you want to put that energy, and that's a space in the industry that's still growing. As you get more people who want to be self-sustaining, have the whole solar and battery backup, you incorporate a bigger battery in the vehicle there, and it just expands the possibilities of what you can do with your energy. OpenADR, real quick, is automated demand response. I mentioned brownouts earlier. All utilities, Duke included, have a system through which they can notify subscribers that, hey, we're experiencing grid problems. If you can, please curtail how much energy you're pulling off the grid and we'll pay you. It's a bit of an older standard. It's XML and SOAP and all that, but they kind of built it once and said, all right, whatever, we don't need to update this, it's fine. There's utility rate integrations. I think I got through everything I wanted to. Really appreciate the opportunity to talk. If y'all want to chat more about EVs or anything else, let me know. You can find my information up here, connect on LinkedIn, all that. So thank y'all.